So the last section that we're going to talk about now is changes in protons. You heard me mention it before. I talked about if we have a change in the electrons, okay, so if we have an atom and we have a change in electrons, let's go right ahead and take a look at that. An atom has the protons, let me just write it this way. An atom, protons equal the electrons. If you get a change in electrons, then you form an ion, okay? Now, protons plus the neutrons equals your mass number, and if you have differences or changes, however you want to look at, in the neutrons, then you have an isotope, okay? So what happens though if we have changes in protons? Well, if we have changes in protons, it's a whole new thing. It's no longer the same atom. It's no longer carbon if you have 6 protons, and it's now changed. And that deals with radioactive decay. Radioactive decay is when you have a change in the number of protons. Now, there are 3 types. It doesn't show over here. Yep, 3 types right there. Really 2, and then the third one is involved in both of them. But we have alpha decay and beta decay. Both of these are particles, okay? Beta is a particle. So an alpha particle is very weak. We show the alpha particle with the lowercase alpha symbol, looks like this. Beta, lowercase b symbol, okay? Now, alpha, both of them are particles. Alpha very weak, paper would stop it. Beta particles, a little bit stronger, heavy clothing would stop that type of radiation. One thing to recognize, and the most important, is to recognize what this particle looks like. An alpha particle is very similar to a helium atom. If you look at helium, it would have number 2 protons and mass of 4. That's what an alpha particle looks like right here, 4 and 2. And this right here is really important to remember. If you can remember the alpha particle having that 4 and 2, then you're going to be okay when we start to talk about going ahead and breaking things down with radioactive decay. Beta acts like an electron. It has 0 for a mass and -1. Both of these things are on the left side, the numbers, 4 and 2 for an alpha, 0 minus 1 for beta. And again, you need to remember these. Both of this is how we describe the particle, okay? The third type of decay, as we're going through it, and we'll come back to those things, the third type of decay is gamma. Gamma is a wave. It's extremely strong, and it's only stopped by a certain element. Now, you might even you might be able to think of what element on the periodic table. It's a metal that can stop gamma waves. If you think about, if you've ever had an x-ray, even at the dentist, they put this apron that has lead in it, right? And lead can stop gamma radiation, okay? So it's very, very strong. Now, again, here's what they look like and just kind of their strengths. Notice I've got my alpha particle, which would have a 4 and 2, beta 0 minus 1, and because gamma is a wave, it has no mass and no number of protons. It'd be 0 and 0, okay? These are the 3 things you really kind of need to be aware of when you go through radioactive decay. So, alpha particle, 4 and 2 on the left, beta, 0 minus 1, gamma, 0, 0. Now, you heard me say there are 3 types, but then I also already said that there's kind of really only 2, and then we had a third. And here's what I mean. There are really 2 types of decay. You have alpha decay and beta decay. Gamma, the gamma wave gets released in both cases, alpha and beta. So if you have alpha decay, what I want you to do is think of if we have a chunk of something and a decay is not anything added to that substance. So that substance is just sitting there and it's breaking down. You've heard of half-lives, we'll get more into that, but decay, it's just sitting there and it's decaying. What happens is a chunk would fly off. Now that chunk could be the alpha particle. And so if the alpha particle, here it is, that little chunk here, the yellow chunk shooting off, then what we have afterwards is a new substance that's lost that little chunk. Okay? So whatever this is, let's call this X. And now, once that alpha gets shut off, we now have a new substance. Let's call it Y. And how can we determine what that new substance is, that Y is? Well, we look at what the alpha particle has for a mass and the number of protons in the nucleus, and whatever that's gone, then we have our new substance. So let's take a look at alpha decay. An example of alpha decay, and I could do any, is let's say Neptunium 240. Now notice how I did write this out. Neptunium 240. Neptunium, you look it up on the periodic table, is Np. Okay? The 240 represents the mass. So 240 as our mass. Neptunium is number 93. Notice nowhere in that description, Neptunium 240, do I have to say 93. Because if it's Neptunium, it has that many protons. Now, if it goes through alpha decay, Neptunium, it breaks down without anything added to it. So we really need to just put that arrow. I put an arrow, meaning we're not adding anything to it. We just have Neptunium breaking down. Now, if it breaks down and goes through alpha decay, we would have an alpha particle being shot off. That alpha particle gets shot off. What is the new thing? Well, you know how I was just describing it. We have a chunk of something, and if that alpha particle gets shot off, then we have an alpha particle and something new. Okay? Well, what is that something new? Really, all we're doing is looking at the upper left corner and the bottom left corner, and it tells you how much mass is shot off. Well, notice that 236 plus 4 equals 240. So that's how much mass is on your new thing. Your protons would be 91. Why? Because 2 are gone. We had 93, and so therefore we have 91. So that tells us what the nucleus looks like, the protons and neutrons, the nucleus looks like on your new substance once it's gone through decay. All you need to do is take a look at the periodic table. Which one is 91? Well, it's protactinium, Pa. Okay? So there's your alpha decay. Let's take a look at beta decay. Beta is that 0 minus 1. So let's just say we have uranium, which has a 92, to, I don't know, 38. Okay? And it breaks down immediately. Immediate breakdown, put that arrow immediately. 0 minus 1, beta particle. No big deal. Now what's new? Well, if this is a 0 on the top, the mass of your new thing is going to be the same as our beginning one, because the beta particle has no mass, so 238. Now because this is a negative 1 down here, then it also would have a 93 as or it would have a 93. It would be Neptunium, because 93 minus 1 equals 92. And this almost acts like an equal sign, the arrow here. Okay? And so we look on the periodic table as to what number 93 is. It's Neptunium. And there you are. Notice that Neptunium has a different atomic number. I wasn't worried about that because it could be different isotopes. But that's alpha and beta decay. Now the key is there is really no gamma decay. The important thing is that gamma waves get released on both alpha and beta decay. You must have the gamma wave being released in both cases. Okay? So alpha beta decay, just know your particles, and if you know your particles, then really to figure out these other things, it's a simple math problem. of course, we don't want to forget our gamma. Now, this is kind of a mess of a screen. Let me very, very quickly do one more here. And let's say we have uranium, dash 2, let me erase that. Uranium 240 undergoing alpha, then a beta. Let's just do that. So uranium 240, which is 92, goes through an alpha. Boom, arrow immediately. Alpha, 4, 2, alpha symbol. What's the new things? 236, doing a little bit of math, 90. Look on my periodic table, TH is number 90, and don't forget your gamma. So it went through the alpha, then it's going through a beta. Well, I can just bring this right on down, 236, 90, 40. And then it breaks down. Well, let me grab a different color just for impact. Beta, 0 minus 1, beta symbol, 236, 91. I look up 91, it's PA. And don't forget your gamma. So there's alpha and beta decay.